So the first category of problem that I want to look at is rolling a dice or rolling two or more dice. And so we're going to roll dice, and we're going to look at the frequency of getting the different numbers from the dice, 1 through 6. And we're going to use the NumPy random number generator, the integer version of the random number generator, to generate our dice rolls. And actually, I'm going to roll the dice many times, 100,000 times in this example. And we're going to plot the distribution and the frequency of the outcomes of the dice rolls. So let's just work our way through this code a little bit. So firstly, I'm going to import NumPy. I'm going to use its libraries. I'm going to use its random number generator, so I need to import that. I'm going to import matplotlib because I'm going to make some plots of the outcomes of rolling the dice, the frequency of the results from rolling the dice. So I need the plotting functions. I'm going to roll the dice one dice. I'm going to roll it actually 1 million times here. And I'm going to, each time I roll the dice, I'm going to record the roll of the dice, the value that I get when I roll the dice in this array here, roll array. That's so I can make some plots, make some graphs. Here's a for loop. So here's a loop in which I'm going to loop round 1 million times. And each time I loop round the for loop, I'm going to throw the dice, or I'm going to simulate throwing the dice. And I'm going to get the outcome of rolling the dice. And I'm going to store that outcome of rolling the dice. So let's look at the two lines of code that do that. This line of code calls the function in the NumPy library that's going to give me an integer, a random integer. And I want a random integer between 1 and 6 because those are the faces of the dice. And so I call the function with arguments that correspond to the lowest integer that I want it to return, and 1 plus the highest integer that I want it to return. So the range here is 1 through 7. That will give me outcomes 1 through 6. It returns a value of 1 through 6 in this case. So it returns the simulated roll of the dice. I call that variable roll. And then I'm just going to add that to my list or my array of dice rolls. So I can later plot that. So if I run that, then it will, well, if I run that and haven't imported the NumPy library, it will crash. But if I first import the NumPy library and run it, it should not crash. And I built an array. I built the results of 1 million rolls of my dice. So now let's look at a few plots. In this first plot, I'm just going to plot the outcomes of the dice rolls. So from 1 through 6 is the vertical axis versus the index of the roll. I made 1 million rolls. So the index of the roll goes from 1 through 1 million. And so if you look upstairs here, I'm just plotting the roll array. Each element is a roll of the dice, and I'm just plotting the outcome of each element in that array. And what do we see on this graph? Well, horizontally, I see my 1 million rolls. Vertically, I see my possible outcomes, 1 through 6. And whilst I can't tell quantitatively whether the probabilities of the different outcomes, 1, 2, 3, 4, 5, 6 are exactly the same. I get a sense from the graph that there was equal probabilities for the 6 different outcomes. So that's one graph. There's a second graph that I made. There's a little more quantitative. So let me talk about this graph. This graph is going to plot the frequency of the different outcomes from rolling the dice. So I rolled the dice 1,000,000 times. It's going to plot how many times, or at least the fraction of times, that I got the digit 1, or I got the digit 2, or the digit 3, and so on and so forth. So it's going to plot that. And it's going to plot it as a histogram. And so when I make this plot, there's actually a couple of function calls that I make. One that's made to NumP to make the histogram itself, and the second one that's made to matplotlib, which is to plot the histogram that I've created. So let's just walk through a couple of steps here. So I want to make a histogram that has 6 separate bins corresponding to the 6 possible outcomes of throwing the dice. So this is the number of bins that I want. And I want to build a histogram out of that. And so if you look here, I'm calling in NumP the histogram function. The first argument in the histogram function is my array of outcomes from rolling the dice. The second argument is the number of bins that I want. I want 6 bins corresponding to 6 possible outcomes. And then the third argument is the range of these bins. So I want them to start from 1 and end on 6. And so that really defines, the second 2 arguments defines the nature of my histogram. And the first argument is the data that I'm going to histogram, that I'm going to make the histogram out of. And so I go ahead and do that. It returns a couple of things to me. This variable YF, that's the contents of each bin. This variable bins, this is actually something I'm not gonna directly use, but it's a variable that tells you the values of the bins, but I'm not going to use it. So I've now got the contents of the bins. I'm going to add to the calculation of the contents of the bins from the calling of the NumP histogram function. I'm going to add the calculation of an error, an uncertainty due to statistical fluctuations on the bins. That's DYF. So that's kind of the uncertainty on YF. And it's just determined by the square root of the number of times I got that particular outcome for that particular digit of the dice. So I'm going to define that. I'm going to define a horizontal axis for my histogram that I'm going to make. So I want it to run from 1 to 6 with 6 bins. So I use linspace to define an array that has that range and those values. And then I'm going to redefine here YF and DYF. I'm going to redefine them. Instead of being the number of times I got a particular outcome and the uncertainty on the number of times I got a particular outcome, I'm going to define them as fractions. So I'm going to divide YF and DYF by the total number of throws of the dice. Once I've done that, all I've got to do is basically plot the histogram. And to plot this histogram, I use a lib function called error bar. It's going to plot a histogram with error bars. I pass it the arguments of the centers of the bins on the horizontal axis, that's XF, the contents of the bins vertically, that's YF, and then the error bars on the horizontal and vertical directions. So I have no uncertainty on the horizontal values, the number for the digit, but I do have statistical fluctuations on the frequency or the fraction of time I get those digits. That's the DYF. So if I make that plot, what do we see? On the horizontal axis, I've got the 6 possible outcomes for the dice, 1 through 6. On the vertical axis, I got the probability of getting each of these values. It's really hard to see the error bars. You can't, because I rolled a million times, and so the error bars are really, really small. But what you're seeing here is, as well as I can tell from the histogram, that the probability of getting each particular digit is the same. They would only differ by statistical fluctuations, and they are 1/6 of the million throws. Each individual digit has a chance of 1/6 of the outcome. And so that's an example of NumPy random numbers, random integers. So as a second example of using random numbers, I want to show you how to use random numbers to calculate what will generally be an integral. So specifically in this example, I want to calculate the volume of a sphere. I'm going to calculate the volume of a sphere of radius 1 unit. Now look, we know the volume of the sphere is 4/3 pi r cubed. So we know the volume of a sphere is 4/3 pi. So we know the answer to this. But I'm showing you this case where we're going to calculate it using random numbers, by throwing random numbers as a technique. And then we can compare the results of the calculation using random numbers as a technique to calculate an integral or volume. We can compare it with the known value for the integral of a sphere, a radius 1 unit, 4 pi. So how am I going to do this calculation? That's a very good question. I'm going to imagine a volume of space, 3-dimensional space, where x, y, and z, the Cartesian coordinates, are going to be in the positive sort of quadrant for all those coordinates. And in particular, I'm going to imagine a region of space for x that goes from 0 to 1, y that goes to 0 to 1, and z that goes 0 to 1. So it's a little cube. It has a volume of 1 times 1 times 1, 1 unit cubed. And we're going to throw random numbers, random x, y, z coordinates into that cube and create random points within that volume. Now, supposing I got a sphere of radius 1 centered at the origin. For each of the random numbers that I throw into that volume of 1 cube of the units, for each of those random numbers I'm throwing into that volume, I could ask the question, is it inside or outside the sphere? So it would be inside the sphere if for that random number, the square root of the sum of the squares of its x, y, and z coordinates was less than 1. Then it would be inside the walls of the sphere. If the square root, the sum of the squares of the x and the y and the z coordinates of the random point that I've thrown is larger than 1, then it's outside the sphere. So imagine, right, you're throwing these random numbers to generate these random points in this volume, and some of them, and you can figure out which one of them are falling inside the sphere and some are falling outside the sphere. So supposing we calculate the fraction of the total number of random points thrown that actually fall inside the sphere. Supposing we calculate that fraction, that proportion. That fraction, that proportion, is the fraction of that cube that's occupied by that portion of the sphere. Now, 1/8 of the sphere is 1/8, a corner, kind of a corner, a hemisphere, 1/8 of the sphere is inside that quadrant. And so the fraction of points that were inside the sphere compared to the total number of points I generated, that would correspond to the volume of that 1/8 of the sphere. And so if I just multiply that that volume by 8, I get the total volume of the sphere in all the quadrants, where x can be negative, y can be negative, z can be negative, and all the possible combinations of x and y and z being positive and negative. And so that's how I'm going to calculate the volume of the sphere by generating random numbers, generating random points in my three-dimensional space. So let's just look at the code and see how I do that. Again, I've got to import NumPy because I'm going to use random numbers. I've got to import matplotlib because I'm going to make a few plots. Let's do that importing. And then let's walk down to this second cell. And in this second cell, this is where I do all the work of counting the volume of the sphere, of numerically computing the volume of the sphere. So I'm going to throw 1 million points into this volume that has a volume of 1, that is a cube of volume of 1. And I'm going to count of those million points that I throw with this variable count, how many of them are inside the walls of the sphere in that quadrant. When I do this, I'm actually going to fill arrays with the points that I throw and the points that are inside the sphere. The main reason I'm doing that is really because I want to make a plot at the end to show you the points that we threw in total and the points that fell inside the sphere, so you believe this method will work. If I wasn't making the plot, I wouldn't really need to declare and fill these arrays. Here's where all the work is done. So again, I've got a for loop, and it's a for loop in which I'm going to loop around 1 million times, and each time I'm going to loop around, I'm actually going to generate a point in the three-dimensional space, in the three-dimensional volume, in the three-dimensional cube. And then I'm going to ask, is it inside or outside the sphere? It's inside the sphere. I'm going to increment my counter. So let's just look at the lines that do that. This line here calls in the NumPy random library package, that function ranF. That's the one that's going to generate a random number that's a floating point number that is limited from 0 to 1. And I'm actually on this line calling it 3 times for the 3 Cartesian coordinates of my point, my x value, my y value, and the z value. So I'm calling them x, y, and z. The x, y, and z coordinates I store in these 3 lists for later plotting. So this is just me storing them to do some plotting later on. If I wasn't doing the plotting later on, I wouldn't need to store them. Here in this if statement, control statement, this is where I make the test. So this is crucial here. I make the test whether the point is inside the sphere or the point is outside the sphere. If the point is inside the sphere, then x squared plus y squared plus z squared, the sum of the squares of its x, y, z components is going to be less than 1. And so if it's less than 1, I increment my counter that counts only the points that are inside the sphere. I increment the counter by 1. I also, as I say, because I'm going to do some plotting, are going to append to 3 other lists of XYZ components, the list of XYZ components of the points that are inside the sphere. So I also build that because I'm going to make a plot out of it. Okay, out of this loop, out of this for loop that we ran through a million times, I'm going to come out with a value of the variable count. It's the number of times that the points out of the million fell into the sphere. And so now all I got to do to calculate the volume of the sphere is figure the fraction of counts that were inside the volume. So that's just the variable count divided by the integer n. That will give me the number of the fraction of counts inside the volume. I cast both count and n, which were integers, as floating point numbers to make sure that I calculate a fraction or a decimal. And then, as I say, I got to multiply that by a factor 2 to the power 3, a factor of 8. That's because I've only really calculated the volume of this portion of the sphere that's in that quadrant where x is positive, y is positive, z is positive. That's 1/8 of a sphere. And so I've got to multiply that number by 8 to get the full volume of the sphere. And so that's what I do here. And then this will be n vol is my value for the volume of the sphere, the numerical integration of the volume of the sphere using random numbers. I'm going to print that out in the print statement, and I'm going to compare it with the known volume for a sphere of radius 1. So let's just go ahead and run that. Take a moment here because it's going around that loop a million times. But if we look, I've got the volume of 4.195, and the analytical value from 4/3 pi is 4.188. They're not exactly the same because my method with the random numbers has a statistical uncertainty in it. The analytical method does not have a statistical uncertainty in it. If I wanted to improve my method, I would have to run more trials. I would have to throw more points. Anyway, this is an example of how to do a numerical integration. In this case, it was the volume of the sphere. I just wanted to show you the associated plot. Here I make a 3-dimensional plot. So the 3 axes in this plot are the x, y, and z axes. And in these plots, I'm putting points, magenta points and green points. I put magenta points everywhere I generated a point. So there's a million magenta points. And then I overlay on that green points everywhere the point was inside the sphere. And so that's what you see here. In green, you're seeing the points that were inside the sphere in this 3-dimensional plot. In magenta, you're seeing the points that were outside the sphere. And it's, you know, this fraction of green points over the total number of green and magenta points that gives me the volume of the sphere.